Okay, so now this lecture will be again rather mathematical, and while I'm not an expert in this information theory behind the neural networks, let's see a little bit why the neural networks learn. And they have to do with something called information bottleneck. So first we will need to define what is information. So let's say that we have some random observations X that are pictures of cats and dogs. And then we have some labels Y that again they are random, they are taken from this random set that is only a cat or a dog. So they are the labels of the images. So we can measure the entropy of each one of the random variables independently, and the entropy of a random variable is defined in this way. So it is the expected value of the information of x, and the information of x is the minus logarithm of the probability distribution of x. So it is the expected value of this quantity with respect to the p of x distribution. Somehow, intuitively, what it measures is how much uncertainty or randomness the variable x possesses. So it reflects how spread out the probability distribution of x is. So yeah, this is this expected value. So it is the entropy of x is minus the integral of logarithm of px with the minus going outside, and then the expected value is with respect with p of x. So it is p of x differential of x. Then we can define what is the conditional entropy. The conditional entropy of x given y. That is how much, well, it is defined in this way. This is the joint distribution, this is the marginal distribution, or the conditional distribution, not the marginal. And somehow it measures the remaining uncertainty in x after knowing y. So if we are given this example of cats and dogs, and you are given the dog label, so how much uncertainty there in the images once you know the label associated to them is dog. And then we have mutual information. Mutual information is a mixture of the two. So it is defined in this way. So this is the joint distribution, and this is the logarithm of the joint distribution, and this would be the marginals, the two marginals of x and y with respect to this joint. And somehow it quantifies what is the shared information between x and y. How much information, so how much knowing x reduces the uncertainty about y, and vice versa, both at the same time. So I've taken these ideas from this blog, and there are some properties that are useful to know. So the first one is that the information of x and y is the entropy of x minus the entropy of x given y. The uncertainty of conditioning always reduces or maintains the uncertainty of x. So it cannot be that knowing something that is related to x. So if we know something that is related to x, the entropy of x has to be smaller than the entropy of x. And if it is unrelated, it cannot increase our uncertainty. So in the worst case, it will remain the same. This is somehow similar here. So the information between x and y, it has to be larger or equal 0. So either we reduce the uncertainty in each one of the variables, or we don't reduce. But if we don't reduce, we never increase that uncertainty. So it has to be larger or equal 0. And then the joint entropy of x and y is the entropy of x plus the entropy of y once we know x. Okay, so why do the neural networks learn? So there is something that is in all data analysis systems, all of them, even included neural networks, there is something called a data processing inequality. That is, let's say that we have this system in which we have a label that is dog or cat or dog, and then we have an image of a cat or a dog, and then we process this image uh, in any way to produce a label that we hope is the same as the input label that generated that image of the dog or the cat. So as you process, so if you consider the vectors associated to each one of the latent spaces of these layers, as you process the data, the amount of information that you have uh, has to be reduced. So you always that you process data, you lose some information. So at the beginning, there was maximum information of the between the image and the label. But then you process a bit, and then the information between your processed data and the label is reduced. And then as the longer you process, the more information you lose. At the end, you will produce some label, and the shared information between your predicted label and the true label will be always smaller. So we can think of this processing as a compromise between two objectives. One is to reduce to compress the information. So to compress the information, we have the input image, and we want to compress the information so that we produce T. This T somehow minimizes the shared information between X and T. So we want to process the information in such a way that, because we know that X is noisy, all these details of the noise given or produced by the noise, somehow they are information, they are variations, and we want the transformed data to lose those details, all those details that are coming from the noise. So that is why we want to compress the data. But we want to compress the data in such a way that this transformed representation can be useful to maximize the information between your transformed representation and your Y. And so the labels that you want to predict. So in one way you want to compress the information, that is removing the small details, but then you want to maximize your prediction capability, that is taking from X the useful facts, or the useful pieces of information that will help you to predict the final labels. So this concept of trying to compress the data but at the same time keeping the good features to predict is what is called the information bottleneck, and somehow it gives you an idea of what is the optimal frontier of solutions that maximize the relevance or the predictability capability for a given value of compression. So this paper here, this blog discusses how the information between X and T, so this is losing details, so how the losing details information progresses over the number of epochs, and how these transform layers can be used to predict Y. So it can be used to predict Y. So the different colors here are the different layers. So this is layer 0, layer 1, layer 2, layer 3. And then how they evolve over the number of epochs. So as the number of epochs progress, what happens is that the first epoch, the first layer learns a lot of information about the input and a lot of information about the output. The other layers, after only one epoch, didn't have time uh, to learn enough about how to compress the data to represent usefully the labels. And the layer 3 depends on how much layer 2 learned, and layer 2 how much layer 1 learned, and layer 1 how much layer 0 learned. So layer 0 did a decent job, but the other layers did not have enough time. So yeah, so they have some weights, and these weights, they do not carry too much information on the output. So that is why our first predictions are relatively bad. And uh, but then as the number of epochs progresses, here in this video you have how these more points are moving, and the loss function is always going down. But with the number of epochs progressing, what happens is that more and more the later layers learn to some useful features about the output. So here it is also represented now for 3 layers instead of 4. So this is the information that is between the input and the output. We see that there is not perfect information, and then how much information we have between the transformed data and the input, and the transformed data and the output. And this is layer 0, this is layer 1, layer 2, and this is a number of epochs. So as the number of epochs go, you see that all these transformed layers, they start from a high amount of information between X and T. That means the network is retaining all the details, but then as the number of epochs progresses, what happens is that it starts forgetting about details. So it has less and less information about the details, and the later layers, they have more and more information about the output. So somehow this is the meaning of this sentence. The most important part of learning is forgetting. So first you retain all the details about the input, but then as the number of epochs progresses, you forget about those details and concentrate on what are the important features to predict the outputs. And that is the process of learning. So and the process of generalizing. You will generalize if you forget about the input details and you get the useful details to or the useful features to make good predictions about your output. So it has been recognized that there are 2 phases in the learning. So in the first phase, here we are representing the mean, and the mean and the standard deviation of the weight updates, so of the gradient of the weights. So these are not the weights, but the gradient of the weights. So what you would expect is that as the number of iterations go, what you will do is to update the coefficients less and less until you don't update them anymore. So this is this decreasing behavior of the gradient updates. And then what you see is that the last layers stabilize more than the input layers. The input layers are still updated more and more. And then there are 2, and this is the standard deviation. So the standard deviation means that at the beginning, the network is concentrated in learning, so in minimizing the loss function, and it has very little freedom to to try to generalize. So it is try to do this fitting. So this first phase, the network focuses on fitting the data, learning coarse pattern and global structures in the input. And the high mean gradient values indicate consistent updates across the layers, uh, reflecting that the network is taking large steps to reduce the error. And the standard deviation is relatively small, meaning that each layer gradient updates are stable and consistent. And then once it has sufficiently minimized the error, what happens is that we enter into a second phase, that is data compression, information compression. So we try to retain only the most relevant features for the task while discarding irrelevant details. So the noisier standard deviations, so here we have more uh, uh, higher standard deviation for the updates, indicate that the network makes finer adjustment to the learned representations, and this is even more for the first layers than to the last layers. So yeah, these layers farther from the output, so closer to the input, these ones here, experience more noise due to the amplification of errors during the backpropagation process. Okay, another way to look at this information learning is through what is called the epsilon covers. So somehow this is a reasoning that tries to address the fact that deep networks tend to generalize better than a shallow network. So the more parameters you have in your network, the more chances you have of generalizing well. So this goes against the intuition that is normal in machine learning. So we will try to address that. So an epsilon cover is, let's say that you have a number of points in some observed space. So these are the blue points. And then we want to put a cover that is, for instance, these red points, such that the distance between any input vector and the epsilon cover, so the representatives that you have in your cover, is smaller than epsilon. This is what is explained here. So the distance between any input point and your representatives is smaller than epsilon. Then there is this epsilon cover hypothesis in neural networks that says that the neural representations are kind of covers. So during the training, the neural networks implicitly construct a representation that acts as an epsilon cover of the input data space. So these representations approximate the input space while discarding unnecessary details. So that is the compression part. And so the compression and now generalization. So the this hypothesis of the epsilon cover connects the idea that connects to that idea of compression in information theory, this information bottleneck, so that the network reduces the input space to a smaller set of representatives, and the level of compression, or epsilon, reflects the network generalization ability. A good epsilon cover balances between retaining important features and discarding noise. Okay, so the old wisdom in machine learning was this one, that is somehow called the old generalization bounds, and you can read more about it in this blog. So the bound says that let's call epsilon the difference between the training error and the generalization error. So the generalization error measures how accurate the predictions of the algorithm, of the network, or the machine model, machine learning model that you are dealing with. Eh, so how accurate those predictions are when you confront the network to ANSI data. So this generalization error, or this difference in the training and generalization error, is smaller than something. This something has to do with what is the size of your cover. So the size of your cover is how many, somehow it is related to how many different functions you can use so that you can reproduce your input space with a smaller than error, with an error smaller than epsilon. So that size is related to 1 divided by epsilon. So if epsilon is a small number, this is large. And then to the number of parameters. So the more parameters you have in your model, this is the number of parameters. So the more parameters you have in your model, the more functions will you will have. So, and these and having more functions may mean that you can adapt. You may choose one that fits your training data, but is not the one that fits your test data. So you don't generalize well. So that is the problem with having too many parameters. The formal definition of it is the VC dimension of your hypothesis. So somehow the VC dimension, that is VC comes from these two researchers. So this D is somehow related, but not a one-to-one to the number of parameters that you have in your model. So, and then number of confidence or the amount of confidence that you want to have, and then the number of training samples. So somehow, if you have many parameters, this size will be large, and if you have very few training samples, then this will be small. So your difference between training error and generalization error will be large. How to get to small errors? You need fewer degrees of freedom in your models, and you need more training samples. So the more samples you add, the smaller will be your training error and generalization error. So somehow this goes against this wisdom goes against having very deep networks, because very deep networks could have a very large number of parameters. So how can we reconcile this practical observation, deep neural networks generalize well, with this common wisdom in machine learning? And somehow it is related, and again the details of this are complicated. I'm not fully mastered them, but they are related to the size of the input spaces and so on. So somehow what we and I will skip all these details, but somehow what we should keep in mind is this idea. So this is related to the information between the transformed data and the input X. So this is called the input compression. So the input compression somehow determines how large this error will be. So if you compress very little, then the information between the transformed layer and X will be large. So you are retaining all the details. If you compress more, so your information is smaller, and then because your information is smaller, the generalized error, or the generalization error and the training error cannot be that different. So somehow it is related to how much information you are keeping. And here it is somehow discuss this connection between the information bottleneck and now these losses of, of, of information. So there are two competing forces. One is the finite sample loss. Finite sample loss means I have a finite number of training data, and then this noise can make. So here what we are representing is the information between your input layers and the input layer and the transform layers, and then here between the transform layers and the output. And there is this information bottleneck limit that we saw before, and there are some properties, some losses associated to them. So one is the finite sample loss. So what is the finite sample bound given by your given examples? And because you have finite samples in the training, you will commit an error that try to reproduce too well that information. So your transformation, your transform layers somehow try to reproduce that too well. The other one is this compression loss. So the compression loss is how much you are representing from your input. So this one is the compression loss, this one is the finite sample loss. So so compression loss is how much I'm losing from the input. The finite sample loss is how much that I'm learning is capable of reproducing the output, any output, and not just the output of my training data. So, and again, I'm not an expert in this area, but I wanted to expose you to this kind of ideas so that if you are interested in them, you can further pursue this topic. So there are two benefits in having deep networks, and somehow they are illustrated here. So what they are they're putting here is how much information there is between the different layers, and so from input to the transformation, and from the transformation to the output. And this as the number of epochs, so it has this behavior that we had, that we showed before. So the first layers, they learn very quickly, but then the next layers, they need the first one to learn, and then they start moving, and they keep more information from the transform layer to the output. But still we see that the more layers we have, so with only one layer, even when we train for many epochs, the information that is kept is not that much. The more layers you add, 2 hidden layers, 3 hidden layers, 4 hidden layers, so the more layers you add, the layers, the last layers, they get closer and closer to the maximum information that you can have. This bound here, 0.7, is the information between X and Y. So you cannot do ever better than the information between X and Y. So between your input and output in your context. And this is the dependence with the number of hidden layers. This is the dependence with the number of training data. So the more data you have, the closer you can get to the upper boundary, and this is with just one layer, I think. Okay, so having many data is good. Having many layers is also good for generalization. This would be all, I think, for the information bottleneck. So this somehow tries to explain why neural networks learn and what is the behavior between the different at the information level between the inner layers of the neural network and the output, and how forgetting about the details of the input data is important, because you are forgetting about the details of the noise.